Okay, so our third topic is acid and base, and it is our fourth fourth week lecture. So in this lecture, we'll see that different definitions of acid and base, and usually, especially Bronsted-Lowry definition, there will be, of course, we will define acid and base by this definition, and along it will come the conjugate pairs of conjugate acid and base. We will see what are those, and also the acid dissociation, water dissociation constant, in fact, to determine hydrogen and hydroxyl concentration in the solution, and how to find pH considering that Kw. We will also see acid dissociation constant and how it is related to strong and weak acids. Later on, we will see, because we know that acid and base, when they react together, they will produce salt and water. So how those salt we can differentiate is acidic salt or basic salt or a neutral salt. And later we know, because of titration acid and base, how and which of the indicator to use to differentiate the acid and base used for the titration type. Okay, so actually we already know that acid is a proton giver or donates proton, and base is that donates hydroxyl ion based on Arrhenius theorem. But here we see we want to see more about the Bronsted and Lowry acid and base, and because based on this Bronsted and Lowry acid and base, acid is a proton donator. Acid is a species or molecule that will give proton, and base is another one that accepts proton. So for Bronsted and Lowry, acid is only based on proton or hydrogen ion. So acid will donate proton, and base will take that proton donated by the acid. So if for a binary compound there is a proton, and there is another thing like for HCl here, we see that from HCl hydrogen will be liberated, and chloride is there also, and the water is accepting that proton and acting as a base. So hydrogen chloride is an acid, and water is a base. So what happens to chloride? What do we call chloride here? Well, chloride is, according to Bronsted and Lowry's definition of acid and base, it is a conjugate base for that acid from where it is coming. Okay, so chlorine, HCl or hydrochloric acid, the chloride is coming from HCl. So the what hydrogen is going as a proton, and the chloride is a conjugate base of that acid of HCl. Alright, and water that accepts proton and acting as a base, and when it accepted that proton, it becomes hydronium ion, H3O plus hydronium ion. So it is an acid of that water. So it is a conjugate acid of that water. So all acids, according to Bronsted-Lowry, has a conjugate acid, conjugate base, and all base excuse me, has conjugate acid in it, or produces conjugate acid, or produces conjugate base. So conjugate acid base pairs we can see more about, like ammonia and water. Water is a very mysterious thing. Actually, it behaves as acid and also as base. When there is a strong acid in it reacts as a base, and when there is a stronger base than itself, it will act as an acid. So in this case, ammonia, although it's a weak acid, weak base, but still it is stronger than water. So ammonia is working as a base, and water is acting as an acid. So it will give one hydrogen or proton to ammonia and produces ammonium ion, and itself, the water molecule itself, becomes the hydroxyl ion, or reduced hydroxyl ion, and it will produce as it becomes hydroxyl ion. It is a conjugate base of that water molecule, that is the acid working as an acid here. And ammonium that is being produced from ammonia by taking one hydrogen ion from water, an acid, so it produces ammonium, and this is the conjugate acid of that base, that is ammonia. So there is conjugate acid and base in everywhere. If we look at this example 15.1, we'll see that ammonia and hydrofluoric acid in fact, hydrofluoric acid is reacting and producing ammonium ion and fluoride ion. So this fluoride is coming from hydrofluoric acid, so of course it is a conjugate base of that acid, and ammonium is produced from this ammonia by taking this hydrogen ion from here, and it is a conjugate acid for that ammonia base. If we now look for some more example, or try to solve this problem, we can see that according to Bronsted acid and base, carbonate ion, it is CO3, and it can produce HCO3 it can produce, and it can produce HCO3. So HCO3. So that means it can take up one hydrogen from someone else, and it acts as a base. It acts as a base and take up one hydrogen ion. So it becomes bicarbonate ion, and when it becomes bicarbonate ion, this is a conjugate acid of this base, and for number B, it goes like this way, that HS, hydrogen sulfide ion, that one it can it can donate one hydrogen ion, or it can accept as a hydrogen ion as well. So it can be based on what is the what is it reacting with. It can act an acid and base both. Ammonium ion, we know that it is already, we have seen in the example previously, it can donate one hydrogen ion, so it is a acid, it can act an acid, and this hydrogen carbonate that we already have talked about. Water, acid and base property. Water in pure state actually is a very weak electrolyte. That means it does not dissociate appreciably. It is very sparingly, very small amount they dissociate, but still they ionize itself. When they are only pure water, still they ionize itself because of their polarity of hydrogen and oxygen. Oxygen is very electronegative compared to hydrogen, so it attracts the electron towards them, and then they produces this hydroxyl and hydronium ion. So when they produce a hydroxyl and hydronium ion, that means one is taking hydrogen, another one have to liberate that hydrogen, and that means when one molecule of hydrogen is taking that hydrogen, it is acting as a base, and that's why it is taking the hydrogen ion, and another one who is liberating is acting as an acid. So they are producing one conjugate acid and conjugate base from that water, both of the water molecule, and this H3O is a conjugate acid of that base, from where that which one takes up that hydrogen, and that the hydroxyl ion is a conjugate base of that acid that liberated the hydrogen ion from it. So when if we want to express this in equation, we'll see that hydrogen, simplify it here. We simplify this H2O, and it produces that hydrogen ion and hydroxyl ion like this. We see that at some point there will be a constant. After some time there will be no more hydrogen and hydroxyl ion increase. That means they will be saturated, and at that point it reaches the constant. And since we already have seen or discussed that hydrogen H2O does not dissociate appreciably, or if they do not dissociate more, so a very small amount they dissociate, we can consider this hydrogen ion H2O is 100%, almost 100, near about 100%, and then or 1. So we can just not consider it, we can just leave it there as 1, and this Kc is depending on the hydrogen ion and hydroxyl ion molar concentration, and this third bracket indicates the molar concentration of these ions or hydrogen or water. So this Kc in fact is the ion product constant of water and at a particular temperature. If the temperature changes, it will change, but at a particular temperature it is always everywhere the same. So this is the ion product constant we call, and then it will be required for many calculation of pH and so on. We will see later. Now one review question says that the Kw value of water at 25 degrees centigrade is 1 × 10⁻14. If the temperature of water increased to 50 degrees centigrade, what is the effect of Kw value? From this equation we see that two water molecule produces hydronium ion and hydroxyl ion that we have seen before, and from the heat of enthalpy we see that is 50 kilojoule per mole. That means we have to provide 50 kilojoule of heat to produce for this reaction to happen. And from when now for this problem, when we are going from 25 degrees centigrade to 50 degrees centigrade, we of course we have increased the heat, and that means we have provided the heat, we have supplied the heat to the system, and then it will increase more, of course, for higher temperature. More hydronium ion and hydroxyl ion will be formed, and that means when this hydroxyl ion and hydronium ion formed, that means the concentration of this will increase, and thus Kw value will also increase as well. For question number 2, the same thing, some equation, same thing, condition. Water poor electrical conductor, we know that it does not dissociate appreciably. So at 25 degrees is very poor electrical conductor that does not conduct the electricity. And then at 50 degrees centigrade, whether it will be more or less. So we know that at 50 degree this concentration is increasing, and this concentration also increasing as well. So when the ion increases, the conductivity will also increase, because the electrical conductivity depends on the ion, right? So it will increase as well. For number 3, we see that it says what is the effect of concentration on of hydronium ion. If the water has a concentration of hydronium ion 25 degrees 10⁻7, if the temperature increases, what will be the effect of concentration of hydronium ion? So so far we have seen for 1 and 2 that increase of temperature increases the hydronium ion concentration and hydroxyl ion concentration. So of course it will also increase. It will also increase. The hydronium ion concentration will also increase. So question number 4, it says the pH of water is 25 degrees 7. If the temperature of water increases to 50 degree, what will be the effect of pH? Now we know that pH, and soon we will see it, the pH is the negative log of the hydrogen ion concentration or hydronium ion concentration. For this case, hydronium ion, for simplified, negative log of hydrogen ion concentration. So if the hydrogen ion increases, the pH would be lower. That means it is more acidic. We know that the pH scale is 0 to 14, and the lower the pH, the stronger the acid. So if the so far we have seen that hydronium ion will increase, so pH of the system will decrease, because increased hydronium ion or hydrogen ion concentration means decrease in pH. Decrease in pH means the scale, it will go towards zero. So it will be decrease in pH. For this case, question number 5, the pH of water is 7 at 25 degrees and 6.63 at 50 degree. What is the effect of temperature increase of the acidity of the water? Now, acidity is the how much of the hydrogen ion or hydronium ion in relation to hydroxyl ion there. So for this case, we see that when temperature increases, hydronium ion increases. But what happens to hydroxyl ion then? Hydroxyl ion is also increasing because this water is dissociating, it producing hydronium ion, and in this due course it will also produce hydroxyl ion as well, because this hydroxyl ion is not going anywhere. It is of course being produced as along with this hydronium ion. So when there is hydrogen, for this water, for water instance, when there is hydronium ion is producing, hydroxyl ion also produced at the same time. So when hydronium ion produced, the pH gets lower, but also hydroxyl ion is produced there. So the acidity does not change. The acidity does not change. The water is still neutral. The water is still neutral. They have same amount of hydronium ion and same amount of hydroxyl ion, so they are still neutral. And we will see from this table that at 25 degrees pH is 7, pOH is also 7, and pH plus pOH is 14. That we will see it later, and we also know from previous time that pH and the sum of pH and pOH is 14 always. So at 0 degree you see that it is not 14, and 100 degree you see it is not 14. That means at 100 degree this is the new normality or neutrality of water is 6.14, and at 0 degree the neutrality of water is pH 7.47. So when it increases to 50 degrees centigrade or 55 degrees centigrade, we see that is 6.63. It doesn't mean that it is water is acidic. It means that it has more hydronium ion available in the system, but still has the same amount hydroxyl ion as well. So pH is a measure of acidity, and then we understand that the higher the acid, the lower the pH. So, and from this equation we can see that pH is negative log of hydrogen ion concentration, and at 25 degrees we have seen for water 25 degrees centigrade, it is always 1 in 10 negative 14. For water at 25 degrees centigrade, it is always 1 times 10 negative 14th. So the Kw value, that is water dissociation constant, is always 10 negative 14th. So for a neutral solution, that I was talking, that hydrogen ion or hydronium ion, for here we can consider hydrogen ion, but just now we have seen hydronium ion for this water thing, hydronium ion. So this hydrogen ion is just a simplified version of this H3O plus. It is just a simplified version of this H3O plus. If somebody writes H3O plus, is also the correct, and it's also the same thing. So when a solution is neutral, we see that hydrogen ion and hydroxyl ion is equal. When acidic, we know that hydrogen ion is more than hydroxyl ion, and an opposite for the basic one. So at 25 degrees centigrade for water, hydrogen ion and hydroxyl ion both are 1 times 10 negative 4th, we also can find it from here. If it is all equal, and then we find we square it, and then we find 1 of hydrogen or hydroxyl ion, we will find this 1 times -10⁻⁷, that is pH is 7. And when it is more hydrogen ion is more than that, the pH will decrease, and if hydrogen less than that, the pH will increase. That means if the pH is more, the hydrogen ion is less. Okay, so a solution, if we say that it is more acidic or higher pH, like 12, the pH is 12 or 13, that means it has very less amount of hydrogen ion, that is more basic. Okay, there are some table for some common fluids that we are very much familiar with every day, and their pH. And pH, we already have seen that it is negative log of hydrogen ion concentration, molar concentration, of course. So pOH is the same way, negative log of hydrogen ion concentration. And Kw value is the product of hydrogen ion and hydroxyl ion molar concentration, and at 25 degrees is always 10⁻⁴ and the pH and pOH is the total of them are 14. Okay, so it says, this is one tricky question actually. I mean where we so far we know that hydrogen ion concentration we can use this for calculation of pH, but if hydrogen ion concentration is not given, only hydroxyl ion concentration is given for a ammonia cleaning solution that has a 0.0025 molar of hydroxyl ion in it. So how can we find the pH of the solution? To find the pH, we must have hydroxyl ion concentration or hydrogen ion concentration. So from here we can see that since hydroxyl ion concentration is given, and for pH we can find the we need the hydrogen ion concentration, we should use the Kw value. So from the previous beginning, we know that Kw is product of hydrogen ion and hydroxyl ion concentration, and at 25 degrees centigrade we know the value is 10⁻⁴, and since the temperature is not given here, we just consider it's 10⁻⁴ at 25 degrees centigrade. So yeah, we will always consider the standard temperature if it is otherwise stated clearly. So we know that Kw value is 10⁻⁴, and hydrogen, and this is the product of hydrogen hydroxyl concentration. So hydroxyl ion concentration, we just use this 0.0025 molar. So from there we can find the hydrogen ion concentration, and if we find the hydrogen ion concentration, we will see the later on we can find the pH of the solution. Okay, my mic is not working. Okay, so now I was talking that we have found the pH of the solution from by finding the pOH, the hydrogen ion concentration of the first. We can also find the pOH directly from this hydroxyl ion concentration, and from therein we can find the pH, because POH and pH is 14 together. So if we find the POH, then we can just deduct it from the 14. That will give us pH of the solution. Now another example, it says that the pH of a rainwater collected in a certain region of somewhere, and it was found that it was 4.82. Calculate the hydrogen ion concentration in the rainwater. So the pH now is given the 4.82, and we have to find the hydrogen ion concentration. So in this equation we can just put the pH, that is 4.82, and of course we have to take the anti-log of this value, so that only we can find the hydrogen ion concentration. So if we take the anti-log of the value 4.82, we find that 1.5 in 10 negative fifth, that is the concentration, the molar concentration of hydrogen ion in that rainwater. So if pH is given, we can just take the anti-log of pH, that is 10 power negative of that pH value, and that would be the anti-log, and that would be the concentration of hydrogen ion in the solution. It is rainwater, it might be a acid solution, it might be a base solution, whatever. We can take the anti-log of it, and we will get the hydrogen ion concentration. In sodium hydroxide solution, another example, in a sodium hydroxide solution, it says that the hydroxyl ion concentration is 2.9 and 10 negative 4 molar. Calculate the pH of the solution. Then now I was saying that we can find the POH just like this. POH is negative log of hydrogen ion concentration, and the value that we found should be deducted from 14, because pH and POH is total altogether is 14. So when we find the pH, that is 14 deducted the POH value, and we will get the pH of the solution. Okay, so it says that another example or problem, it says that water undergoes autoionization as shown. We have seen it a long time, previously, and is write the expression for the ionic product of water, Kw. So what is the ionic product constant of water? For Kw, it is the hydrogen ion concentration multiplied by hydroxyl ion concentration over hydrogen the water concentration. But water, it does not ionize appreciably, or very small amount, so we can just leave the water. So Kw will be equal to hydrogen ion concentration multiplied by hydroxyl ion concentration, that we have seen before. Okay, at 42 degrees centigrade, the value of Kw is 3.46 times 10 negative 14th. Okay, calculate the pH of pure water at this temperature. Okay, so it says that at 42 degrees centigrade we have the Kw value. So how can we find the pH of that water? Well, Kw, we have said, or we discussed, is the the product of hydrogen ion and hydroxyl ion concentration. And water at any temperature, it will be dissociated, and if it dissociated or autoionize, it will produce equal amount of hydrogen ion and hydroxyl ion. So Kw is hydrogen ion equal to hydrogen ion concentration and hydroxyl ion concentration, and that hydrogen ion and hydroxyl ion concentration is equal amount. So we can just consider hydrogen ion, and that will be squared, right? Hydrogen ion equal to hydroxyl ion amount. So we can just consider Kw is equal to hydrogen ion concentration squared. So from there we can find the hydrogen ion concentration of the water, and in that case we can find hydrogen pH of the water very effectively or easily. Continue with the problem 1, that it says that at 75 degrees centigrade, 0.000470 mole per liter of solution of sodium hydroxide has a pH of 11.36. Calculate the value of Kw at this temperature. So for this, Kw value is required or asked, and then we have only two clues, that is what is the concentration of the sodium hydroxide solution and the pH of that solution. So and also it is at 74 degrees centigrade. So the pH at of 11.36, from there we can find the hydrogen ion concentration easily. Just take the anti-log of this pH so that we can get the hydrogen ion concentration, and from this concentration of the sodium hydroxide we can find the hydroxyl ion concentration, right? Because sodium hydroxide is a very strong base, and it dissociate fully. So strong acid and strong base, they are strong because they dissociate fully, they ionize fully in the completely they ionized in the water or the aqueous medium. So for sodium hydroxide, it will dissociate or ionize fully, and then it will produce 0.0470 mole per liter of sodium ion, and also hydroxide ion, OH negative ion also. So from there we know that it will be 0.0470 mole per liter of hydroxyl ion, and then from 11.36, anti-log of 11.36, we will find the 10 powered in 11 negative 11.36 of this hydrogen ion concentration, and from there we can find the Kw, because it is easy. Kw is hydrogen ion concentration, hydrogen ion times hydroxyl ion concentration, molar concentration of that. Okay, once we find the Kw value at 75 degrees centigrade and 42 degrees centigrade, we should be able to know which one, this dissociation is endothermic or exothermic reaction. If it is at 75 degrees higher, that means if we provide more temperature or more heat, then it will dissociate more. That means it will take more heat to be dissociated, and that is what endothermic reaction is called. But if it does not take the endothermic, if it is opposite to that, that means if it produces heat when it is dissociated, it should be exothermic reaction. So if it is exothermic and we put more heat, it will not dissociate more, it will dissociate less because of this the shortlist principle. Okay, so now we go to another one, the strong acid and base. Strong acid and base, that was just said that they dissociate or ionize fully, that in the water or aqueous solution, like perchloric acid, sodium hydroxide, there's a strong base, perchloric is a strong acid, sodium chloride, HCl, these are strong acid also. So from this list we can find some strong acid and strong base. From this list they dissociate fully in the aqueous medium. So weak acid and weak base, they do not dissociate fully, or they partially dissociate. Only small amount or a small fraction of that acid dissociate to produce the hydrogen ion, or a small amount of the base dissociate to produce hydroxyl ion. So they are weak electrolyte, as of course, because there is not enough ions. So they do not conduct the electricity strongly, so they are weak. And also from the low K value, that is the acid dissociation constant value, the higher the Ka value, the stronger the acid is. The higher the Kb value, the stronger the base is. So if their dissociation is high, the Ka or Kb will also be high, and then they will be stronger acid and stronger base. Ka stands for acid, Kb stands for base. So strong monoprotic acid, from here we see that they dissociate fully, appreciably. From here both will produce hydrogen ion and one conjugate base of its conjugate base. And for weak monoprotic acid, most of the acid will be undissociated, only small amount of hydrogen ion and the base will be produced.